Let's talk about some really cool physics. The cyclotron, which is a type of particle accelerator, and perhaps in the name it is not very hidden, it is cyclic or cyclical-like. Before its creation, we did have the Cockcroft and Walton generator, but this accelerator was pretty remarkable. You can make it pretty small, and of course, the bigger you create it, the larger the distance that the protons or charged particles can transfer or move through. There were contributions to the development of the cyclotron by Max Steinbeck and Leo Szilard, but their work wasn't really patented or published, and so the development of the cyclotron by Ernest Lawrence was ultimately the one that was awarded the patent, and number 2, the Nobel Prize in 1939. The original cyclotron was really small. It was only 11 centimeters in diameter, and throughout history they developed them at a larger scale. My favorite story in history about the cyclotron is that after the development and of course the Nobel Prize win, many other universities around the world developed their own, including France. A name that you might be familiar with, Frédéric Joliot-Curie, did develop his own, or he was in charge of one in France. Frédéric stood his ground. He wasn't going to allow the particle accelerator to be used for anything in the war efforts, especially after France was occupied by Nazi Germany. Although it is not proven, there were a lot of rumors that Frédéric in fact did a lot of work in sabotaging the Nazi regime in the development of atomic bombs and nuclear knowledge by sabotaging this said accelerator. But how does a cyclotron work? The design of it is pretty simple but ingenious all the same. It is quite literally a spiral with magnetic fields to bend the charged particle, usually a proton in this case, and an electric field in between the gaps. If you have any understanding of physics, you know that the electric field in this direction means, well, okay, the proton will be accelerated in one direction, but if you go to the other, it's going to be pushed back in the opposite direction. What gives? This is why the thing that is creating the electric field is a frequency generator, or sometimes known as an oscillator. And so we do need to tune our system to know at what frequency we basically flipping that electric field, so that when the proton travels across the gap, it's sped up. We can do a little bit of maths on this. Classic Newtonian physics, F is equal to ma. And because we're going through a circular motion, there is a centripetal acceleration associated with this. A is v squared over r. Another equation for the force that is being experienced by the charged particle Q has a relationship with the magnetic field. Velocity times the magnetic field B. This means we can just equate our two F's, rearrange the equation to find V on its own, and have a singular expression for it QBr over m. Use the charge of the particle, most than likely our proton, the magnetic field, the radius of our traveling particle, all over the mass of the proton. Now we have another relationship for speed. Well, speed is distance over time. It's moving in a circle. The circumference of a circle 2 pi r over the period, the time it takes to complete that circle. Rearrange the equation to find t on its own. Substitute for v. We have an expression above. The two r's cancel as we have an r above and below. Let me move the mic down so you can see our final expression for frequency. After all, frequency is just the inverse of period. We can also extract a useful kinetic energy equation out of this. Kinetic energy, half mv squared. From our previous lines in the other whiteboard, we can substitute an expression for v. Just don't forget to square it. Multiply it all out, and we have an expression for the kinetic energy. One of the masses did cancel there as well. Another step further is we could calculate what the velocity of our particle is by rearranging the classical kinetic energy equation, root 2 times kinetic energy over m. Obviously, we'll take the positive answer because the speed would be positive. So let's say we grab our cyclotron and we say, well, our magnetic field is 1.75 Tesla. That's a really big number. And the maximum radius, because obviously the cyclotron path is going to be increasing outwards, is 0.3 meters. And we're dealing with a proton. Can we calculate the frequency, kinetic energy, and the velocity? Hell yes, we can. I pull out the equation that I derived earlier for the frequency. I have all the numbers. The charge for the electron, the magnetic field 1.75, 2 pi is just a number, and the mass of the proton, also just a number. We get 26.67 megahertz, or 10 to the power of 6. We also have the kinetic energy equation. We have the magnetic field, the maximum radius, i.e. we're calculating the kinetic energy of the particle at the bombardment chamber, at the end of its story. That's why the radius is the maximum value we take. And we get 2.205 by 10 to the minus 12 joules. You can convert that to electron volt, but I'm going to keep it because I can calculate the velocity this way, and I get its speed to be 5.25 by 10 to the power of 7 meters per second. At the moment, It hits that bombardment chamber. It's finale in the journey. I covered a lot with you in this short video. I did the history of the cyclotron, I did a whole bunch of derivations, and I did a practical mathematical example. All condensed in these couple of minutes. I hope you learned something really interesting. Stay curious.